July lectures in physics, for those of you who are coming back. Actually, it'd be lovely to see how many of you have actually come to all 4 lectures this year. Yay! Congratulations to all of you. That's a huge proportion, actually. Hands up if you've made more than 1. Excellent. That's inclusive of the criteria. That's an inclusive criteria. If it's your first ever July lecture, if you're willing to, can you put your hand down?
Aww.
Welcome. Oh, look, so Tony's round of applause from the rest of the audience. Very nice. My name's Dr. Susie Shee. I'm Associate Professor here in Melbourne Physics. I work in the field of accelerator physics, which is like particle physics, but I design the particle accelerators. You're welcome to come and chat to me about that afterwards. And for the last 3 years, I've been the curator of the July lectures in physics. This year's theme is the extremes of physics, and we've seen already a number of different ways of doing that theme through the extremes of light, the extremes of dark galaxies as we had last week, and at the start we also had the extreme search for dark matter. And this week we have Associate Professor Katie Auchettl, who, have I pronounced that correctly? I'm sorry, no, I've done it incorrectly.
Auchettl.
Auchettl, I will get that one day, sorry.
All good.
Associate Professor Katie Auchettl will be talking about the extreme states of the life and death of stars for us. Now, just before we get going with the lecture, I would like to acknowledge the traditional owners of the land on which we hold these lectures and work and teach and research, the Wurundjeri people of the Kulin Nation, and just acknowledge the first people of this country, also as the first scientists and first astronomers, which is extremely relevant to tonight's lecture. I don't want to take up any more of your time. I'm going to hand over to Katie. Thank you very much for giving a lecture for us, Katie, and welcome.
Thank you.
You've unmuted.
I've unmuted.
Excellent. Over to you.
Awesome. Hi, everyone. So hi, everyone. I'm so glad to be here today to be able to talk to you and go through this journey together where we explore essentially the life and death of stars. Here I will talk about how we use these beautiful objects shown here, as well as other extreme astrophysical phenomena, to map out the properties of not only the star itself, but how it died and what it leaves over. But of course, before we delve into understanding these beautiful stellar crime scenes, let's take a step back and start from the very beginning of the life of a star. So we're lucky being in the Southern Hemisphere because we have some of the darkest skies anywhere in the world. And we have some of the clearest view of our own Milky Way and its nearby galaxies, the large and small Magellanic Clouds. So while in the centre of Melbourne, we may not necessarily get a view like this, we do not have to travel far, or even to New Zealand, to be able to see the sky glittering with the thousands of pinpoints of light. But what is special, at least to myself, about this beautiful picture is that each and every one of those dots in this image is a star. Each of these stars are unique. And like humans, they live their lives are fascinating, but their deaths are even more spectacular. But first, let's touch on what powers these stars and makes them bright in the sky, and what fundamentally leads to the beginning of the end of these fascinating objects. So stars are born from clouds of hydrogen and helium. As such, the lifetime of the star depends on the amount of fuel or hydrogen in helium available for the star to devour. And so this also depends essentially on the rate at which that star devours that material, or what we call the rate of energy loss. So of course you didn't expect to do equations, but I promise we'll get to the pretty pictures very quickly. And so another way to think of this is essentially that the lifetime of the star depends on the mass of the star divided by the luminosity, or how bright that star happens to be. And so from looking at a large number of stars where in our universe, we've actually measured the masses and brightnesses, or luminosities, of a large number of stars in our Milky Way. And what we actually find is that we can describe it by this relationship here, where essentially the luminosity is proportional to its mass, times 3 to the power of 3.5. So you don't have to worry about the numbers or what that means, but we can actually put this back into our nice equation and we can actually simplify it, right? Which gives us a nice equation we can look at. But it's Friday evening. We don't have to do maths today, right? So what does that actually mean? Well, what that equation actually implies is that the more massive a star happens to be, the more hydrogen and helium, which it is made of, the shorter the lifetime it will actually be. But now that we know that the mass is intimate, or the amount of fuel is intimately connected to its life, what actually powers or makes a star bright? Well, this process is actually called nuclear fusion. And so nuclear fusion is the process in which the nuclei of two atoms come together to create a new atom or a new element. And so nuclear fusion is the lifeblood of a star, and the enormous luminous energy of the star comes from this nuclear fusion processes that occurs within the belly of the star itself. Without this process, these stars and our very own sun would not be able to shine. Currently, both our sun and all those pinpoints of light shown in the image previously are currently converting hydrogen and helium into heavier and heavier elements using nuclear fusion. And so the light that we can actually see from our own sun is essentially the energy that is released from this extreme and fundamental process. However, exactly which elements are actually produced within the belly of a star depends highly on the mass of the star itself. And so for the most massive stars in our universe, which corresponds to the ones that have a mass of at least 8 times that of our own sun, nuclear fusion allows these stars to form heavy elements all the way up to iron, so the same iron that you have in our blood. And so what it does, it converts hydrogen into helium, carbon into neon, oxygen into silicon, and all the way up to iron, producing kind of an onion shape of elements that we have in this picture. However, once the iron core has actually formed in the belly of the star, this actually marks the beginning of the end of the star itself. And so when this iron core becomes heavier and heavier and becomes at least 1.5 times the mass of our own sun, the core is unable to support its own weight against gravity, which is constantly trying to push against it. And so what happens is that the core will actually begin to collapse. And so here, when it collapses, the outer layers of the star will initially begin to collapse along with that iron core, and they'll rebound with an enormous release of energy and are thrown violently outwards in what we see as a supernova explosion. These violent ends mark the end of one stage of a star's life and the beginning of its new phase in its life after death. And so these violent ends of the life of the star have been fascinating astronomers as long as we've been looking towards the sky. And while only a handful were actually discovered in, say, the 1800s and early 1900s, our abilities to detect these extreme events has rapidly evolved, as you can see here, where each blip of light corresponds to the discovery of these stars going not so quietly into the night. So due to the wide variety of telescopes, similar to your camera, but with a much bigger or much larger lens that views the sky in multiple wavelengths similar to what you and I see in, right, and that are located across the world and also in space, we're able to monitor the sky every night in search for these extreme luminous bursts that indicate that a star may have died. And so in fact, here are actually a few images of supernova that we've actually detected quite recently. As recently as 2 nights ago, using an optical telescope in Hawaii called the Pan-STARRS telescope that sits upon Mauna Kea, which is located on the Big Island of Hawaii. And so what you can see here in these images, which are highlighted by the green little arrows or little points, is essentially this brilliant burst of light associated with a supernova, indicating that a star had reached the end of its lifetime. And so one thing you might notice is that these supernovae can actually briefly outshine their host galaxies where they live. And they actually can radiate more energy than our own sun will radiate in its entire lifetime in a matter of days to weeks. And so when we see this signature here, what we tend to do, astronomers are usually on the case pretty quickly, right? And what they do is that they utilize a vast network of telescopes located on the ground and in space that will cover not only the visible wavelengths that you and I can see in, but in wavelengths from gamma rays to X-rays and all the way down to radio, right? We look at it in any way we can. And so with these instruments, we can actually watch the star or watch the crime scene, the stellar crime scene, unfold in front of our eyes. And we can essentially watch that violent death of a star in real time. And we can then try to piece together what happened and why. And so what do the initial stages of a star's death look like? Well, here I can show you essentially a profile of the first few weeks after a star has died. On the left, we have how bright the supernova changes as time goes on, while on the right, we have how that emission from that supernova changes as a function of visible wavelength, which allows us to see whether it emits in more light, in more bluer wavelengths versus those that are in more redder wavelengths. And so as you can see, as it gets brighter and brighter, we find that the source is very, very blue in these very early stages of its evolution. However, as it begins to reach its maximum brightness, we find that other colours begin to dominate this picture, where essentially emission in green, in yellow, orange or red starts to play a predominant role. And so like humans, these stars have their own unique personalities and descriptions, and whether they emit in blue or red or somewhere in between tells us a bit about the star before it actually died. And so one of the most famous examples where we actually captured a massive star undergoing a core collapse supernova explosion was actually one that occurred right in our own galactic neighbourhood. And so this supernova was called 1987A, and it's called this because it occurred in 1987, and it was the first supernova we detected that year. Astronomers are not very imaginative when it comes to naming. So this supernova occurred in the Milky Way's nearby galaxy called the Large Magnetic Cloud. And living in the southern hemisphere, we're actually lucky enough that we can actually see the galaxy by eye, and when the sky is dark enough. And in fact, when this massive star died, when it actually went off in its supernova explosion on February 24th, 1987, the luminosity or brightness of this explosion was so much or so extreme that even by visible by your own naked eye, could you actually see that supernova occurring. And for many, many months after the original explosion. And so we've been actually incredibly lucky that this supernova occurred so closely to us, because we've actually been able to kind of study and watch the evolution of this supernova in real time, allowing us to kind of piece together the events that led to its violent end. And in fact, here you can actually see some snapshots of the expanding shock front of stellar material ploughing its way into the surrounding environment, sweeping up everything in its path and glowing brighter and brighter. And so it's kind of like we have front row seats to this cinematic production of the final stages of the star's life. However, this is not the only supernova that we've been able to see so close. And as of only a few months ago, we recently detected this supernova here, called Supernova 2023 IXF. And this actually occurred in this very beautiful galaxy, very beautiful spiral galaxy called the Pinwheel Galaxy. And what's special about this supernova in particular is the fact that it's the closest supernova detected in the last decade. And so this has actually given us another opportunity to study up close the final stages of this star's life. However, as we're all on a mission tonight to try to piece together what happened in the stellar crime scenes, we should now start asking a few questions to try to understand what led to these spectacular events. And so you're probably wondering, before we see these beautiful bursts of light, is there a signature that may give us a hint that the end is nigh? Well, in particular, does the star do anything strange before it leads to its death? And so the answer to that question is actually yes. So like the poem by Welsh poet Dylan Thomas, stars do not go gently into that good night, right? They give us a hint of their impending doom, and they do it in a few different ways. And so one of the more spectacular ways in which they start is that they actually start to shed their outer layers in sometimes a very spectacular fashion. And this can actually start thousands of years prior to their actually expected death. And so here's one of the more famous examples of a star nearly 10 times the mass of our own sun, right? Actually illuminating the interstellar dust and material that was thrown out by the star long ago and now surrounds the star itself. And so these outbursts were had a significant amount of mass from the star that was thrown out, and we can find that they can actually expel huge amount of material into their environment. And that can become much more frequent and more extreme as it gets closer and closer to its final days. And so we actually see these outbursts only a few weeks or even days before the star's death, like what we actually show here, where at 60 days, we see nothing that could indicate to us that something was about to occur. But around 40 days before disruption or before the explosion, we just start to see hints that the end is coming. And then suddenly, we see the final explosion, which peaks over on this side part of the plot. However, stars in their final throes are not the only sources out there that produce these bumpy, what we call light curves, right? A light curve is just essentially brightness as a function of time. And so in fact, we actually see a wide range of astrophysical phenomena whose brightness actually varies with time that could maybe mimic the signature of impending death. And so, then how do we know that we're actually observing, or what we're actually observing is actually associated with the death of a massive star? Well, in a number of cases, we've actually saw the star before it died. Here is an image that was taken by the Hubble Space Telescope, which is essentially an image of a galaxy that hosted a supernova called Supernova 2019 YVR. And this supernova in particular resulted from the death of a very massive star, at least 15 times the mass of our sun. And so you might think, great, right? If we're lucky enough that we'll actually get an image like this, which was taken serendipitously 2.5 years prior to the actual explosion, that maybe if we have this all the time, right, it should be easy to connect the nature of a star to exactly how it died. However, this method actually requires us to be quite lucky in the sense that someone had actually took an image of a part of the sky where we actually expect a supernova, or where a supernova's location will happen to be. And for a lot of supernova, this is just not available, right? Really, only the supernova that are very close to us can provide us with that opportunity. As such, we have to work out other ways to try to determine what we are actually seeing is actually arising from the death of a massive star. And so at the top, we have what it looks like after its death. And at the bottom, we can see the little star, this little pinpoint of star there. And so actually, what we can do to try to work out if we don't have that images is that we can actually look at signatures of the star itself. And so remember previously I showed how as the supernova gets brighter, it becomes bluer with time before these blue wavelengths fade and become dominated by other parts of the visible spectrum. Well, we can actually also find that we get specific bumps and wiggles in what we call spectra, right? Which is just the name we give for all those colours that we're looking at. And so there are very specific features that correspond to that of a massive star. And so these are what we actually expect from massive stars, right? That are very typical and that we're very different from what we expect from the very top image, which happens to come from explosion of a low mass star, which we don't even touch on in this talk today. And so what you can actually see here on the right is actually the signatures that we actually detect from that the closest supernova that we've seen in the decade, the 2023 IXF. And what you can see without knowing anything about what's actually plotted there is that there's some lines that match up, right, that I've highlighted in this thing. And the only way that you can actually get this strong bump that I particularly highlight is that it can only occur from a star that has at least 8 times the mass of our own sun. However, even though I've now shown you ways in which we can try to investigate the death of a star using these cases of stellar death, we're actually still quite limited in exactly understanding the final stages of the life of a star. Usually we have to be lucky that the star died and had to be very close to us for us to be able to probe these final stages. However, usually we're actually not that lucky, in that supernova actually usually don't occur this close to us and are actually not easily visible by the naked eye, like some of the examples I had shown you previously. And in fact, supernova, or the death of stars nearby, actually don't occur very often. In fact, they're actually really quite rare. So the fact that we've actually had a handful of them has been quite amazing, and I'm very glad that I live in this time to be able to study these. And so on average, we actually expect between 2 to 3 supernovae per century per galaxy out in our universe. But even in our own Milky Way, or even nearby galaxies, we have seen much, much less than this. In fact, in our own Milky Way, we've only detected 8 supernova in 2,000 years, much less than the expected 2 or 3 per century per galaxy we expect. And so actually some of these were actually detected by the world's first astronomers, the Indigenous Australians who actually observed some of these. And so because they're actually so rare, this makes it quite difficult to study many aspects of stellar death directly. So what can we do? Well, there's actually another way to kind of get around this issue. And instead, we can actually look at the leftover remains of stars that died hundreds to thousands of years ago. And so these beautiful objects here are called supernova remnants, and they're actually the long-lived structures that result from a supernova explosion of a massive star that occurred way before our lifetime. And so in our local galaxies, there are hundreds of these beautiful objects, and thus they provide us with a very unique opportunity to try to study stellar death in a completely new way. Because now the stellar crime scene, which was previously a pinpoint of light in a galaxy far away, is now spread over our sky, right, in these extended structures. And so that actually provides us with an opportunity or a different way to peer inside the properties of the star and the nature of the explosion in significantly more detail than what we could get before. However, if these objects occurred hundreds or 1,000 years ago, you're probably wondering, well, how do we know supernova remnants result from the death of a massive star? Well, there are a few key things that we can try to look for to be able to pinpoint that connection. The easiest way to determine whether these beautiful objects arise from a core collapse of a massive star is essentially the detection of something called a neutron star, which is essentially a very dense core that is left over after the explosion of a massive star. These objects are some of the most extreme objects in our universe, and they're usually born rapidly rotating, which means they can produce their own luminous multi-wavelength emission, which makes them easy to spot in the hearts of these beautiful objects. And so here is one of the more famous examples of a neutron star called the Crab Nebula, where we can actually see it rapidly rotating, and this produces a beautiful nebula that surrounds it, coming from that extreme magnetic field that these neutron stars actually exhibit. This image blows my mind every time I see it. However, not all neutron stars look like this, but rather what we see is something more that looks like these images shown here. We see at the heart of a supernova remnant, or the leftover remains from stellar death, is essentially a pinpoint of light that glows incredibly bright. And that indicates to us that there might be a neutron star there. And so of the hundreds that we detect in our local universe of these supernova remnants, about a third of these remnants actually have these extreme and incredibly compact objects at the heart of these supernova remnants. And so sometimes this kind of classification is quite easy, right? That we can say it had to come from a massive star, because we can see the neutron star glowing easily at the center of our supernova remnant. But sometimes it's not that easy. Like the top example up here where I had to draw a box to highlight where it is that we have to sometimes look even closer towards the center to work out if there's actually a neutron star there. However, the fact that as neutron stars cannot be produced in any other method except in the core collapse of a massive star, right, the detection of this object at the heart of these beautiful extended structures, right, tells us that this must have arisen from a massive star that died. But since not all massive star explosions produce an observable neutron star, remember I said only a third of the local remnants actually show this, right? We need other methods to try to determine whether this actually comes from a massive star collapse or not. And in fact, we can actually do this by looking for specific signatures of different elements that can only be produced during the lifetime of a massive star. And so if we see these signatures of these elements in the light that is emitted from the extended structure we're observing, we can actually measure the amount of these elements that were produced and determine whether that is consistent with what we expected from a massive star or not. And so here I have an example of a very famous supernova remnant that resulted from a massive star called Cassiopeia A. And what we can see, as I've broken up into the different colours, essentially is that it produces a lot of the elements that we expected from nuclear fusion. However, sometimes we're actually not able to measure these signatures. And so what other method is actually available to us to be able to work out, is this a massive star or not? Well, there's actually a method that everyone here can actually use, and actually the first step that I tend to do when looking at these beautiful objects. Because what this method actually relies on is looking at the shapes or the morphologies of this extended emission. And so what we find is that when we look at all these objects, those that came from the death of a massive star tend to be more asymmetric and elliptical in shape. So they look a little wonky, right? And so here, what we find is actually some examples on the side here, which laser pointer doesn't work, but that's okay, on this side here, right? Where we actually find that they all look a little bit squished, right? They're not kind of like a little bit of football shaped, a little bit kind of not perfectly circular, right? And we can actually compare these to the explosions of those low mass stars that come from the stars that explode that are less than 8 solar masses that we don't talk about. And if you look at those, which are on the other side of this plot, is that they're much more circular looking, right, in comparison to what we see on this side. And so just by eye, you can already visually, if I showed you an image, you'll be able to classify, is something a core collapse or is something not? And so now that we know or have methods to be able to say something came from a massive star, we probably want to know some things about the star itself, such as its mass, to be able to connect what we had seen in terms of the leftover remains to the type of star that actually died. And so one question could be, what is the masses of the star that actually produced this? I had said to you, it has to be above 8 solar masses, 8 times that of the sun, but I just told you that. Can we actually go measure that to prove it? And so previously I said that when we look at supernova explosions itself, we usually try to look and search for images of the star before the star exploded, all right? To try to give us a hint or indication about the nature of the star before it actually died. And so through this study, we have found that there's a wide range of masses of stars that actually explode in these very extreme events. And we find that they range anywhere between 8 times that of our sun, all the way up to 20 times that of our sun. But we were talking about supernova remnants, right? And so these occurred, a star exploded thousands of years ago. So what happens in the case when we didn't see the star before it actually exploded? Well, for our supernova remnants, which are the leftover remains of a star that died hundreds and thousands of years ago, we have no direct way to be able to determine the star before it died, right? Because we weren't around or had the ability to be able to do that at a time. So what do we actually do in this case? Well, what we can actually do is look at all the neighbouring stars that are surrounding the leftover remains, and we can actually use the known masses of those neighbouring stars in that immediate vicinity of the supernova remnant and say that they are likely an approximate representation of the masses of stars that explode, producing those beautiful extended objects. So we're looking at our neighbours to see whether we are similar or not. And so the reason why we can do this is essentially that massive stars do not travel very far from their birthplaces, right? From their original from their birthplaces. As such, we can actually use this method quite reliably. And so here I have an example of supernova 1987A again, where essentially we were actually lucky enough to see the star. And what we actually do is then pinpoint and look around at the stars in the immediate vicinity. And we find that they have a mass, all have approximately a masses of around 15 times that of our sun. And so that suggests that supernova 1987A should have come from an explosion of a star that big. And in fact, when we compare it to the star we saw, it's actually true, right? So it tells us that we can actually confirm, this provides us an additional confirmation or a way for us to really probe things we had not seen. But this is only one supernova remnant. What about the others? Can we use the same trick? Well, in fact, we can actually do this for many of the supernova remnants in our nearby galaxies. And so here is essentially a radio image of the Small Magellanic Cloud, one of our neighbouring galaxies, which again, I said you can actually see by eye in the southern hemisphere. And what the cyan circles that you have on this image corresponds to the locations of supernova remnants, or the remains of stars that died long ago. And so doing that same trick as before, where we looked at the masses of the star in the immediate vicinity that surround each remnant, we actually find similar signatures. We find that we can connect the masses of the stars to the explosion that we observe. And so in this example, in particular, we find that this object must have arisen from a star that was at least 10 times the mass of our own sun. But this is only one example, and I can look at all of them, which is what we had done. And what we find is that these objects come from a wide range of masses, with some of them being small here being relative, right? That only about 10 times the mass of the sun, up to approximately 50 times the mass of the sun. So there's a whole range, again, we can actually look at that. And so we actually can see, we now know that these stars can explode in these dramatic fashion, and that mass can produce very different signatures. So now that we know that they arise from massive stars, and we know the masses of the type of stars, so we know a little bit about the star that explode, the next step is to understand how exactly did they die, right? How did these massive stars actually explode? Well, previously I had said that massive stars produce these very asymmetric and elliptical or kind of wonky shaped supernova remnants. And what I showed on this plot is that when I showed this plot, you're probably wondering, well, why is that the case? Why is the massive star lead to this behavior or this shape? Well, one thing you could think of is maybe it's inherent to the explosion itself, or maybe does it have something to do about where they actually live in our universe? And so the first case is a little complicated, right? So let's look at the second case itself. And so, does where a massive star live affect how they actually die? And so we can actually go back to our beautiful nearby galaxies, the large and small Magellanic Clouds, and look at the remnants in these galaxies. And so why do we do this? Well, one, there's over hundreds of them in our galaxy, or in these galaxies, which allows us to really understand how different environments or locations actually affect the explosions we see. These different galaxies also have very different properties. And so we can actually work out how their locations and the properties of their locations or their environment can actually dramatically affect the outcomes of their collapse. So similar to how you think of that the environment on the east coast of Australia is quite different to what we see at the centre of Australia or on the western part of Australia, right? They actually have quite significant effects on, for example, do we wear jackets or not in winter, for example. And so by looking at these objects in different galaxies, and many of them, we can actually understand how environment actually affects the leftover remains of a star. But how do we actually do this? We can again look at the shapes. We go back to the shapes of these beautiful objects. And we can actually determine whether they're quite circular or quite asymmetric and wonky in shape. And so looking at these images, you probably already know the answer without me telling you. But let's make the step through this. And so what we actually find is that environment dramatically affects the explosions we see. We find that it actually depends dramatically on how metal-rich or metal-poor the galaxy may be that it lives in. And so what we find is that the more metals that are in the environment that birth those stars, or actually leads to a more asymmetric death than if you're in a metal-poor environment, or a metal-rich environment, we should say. And so now we've touched on the masses of the stars that die, how they die, and how the environment actually affects their death. You might be wondering if their death leave anything over beyond these beautiful extended objects. Well, I'd already given you the hint to this before and touched on it briefly, but essentially a death of a massive star can leave over those neutron stars, right? Which is that leftover core of the massive star that had died long ago. And I had mentioned that these objects are some of the most extreme objects in the universe. But what makes them actually extreme? Well, for one, they're extremely hot, over 100 times hotter than our own sun. They're also incredibly compact, and usually they only have a radius of about 20 kilometers in size. However, they can be as heavy as our sun. So imagine taking our sun, which is huge, and then squishing it to the radius of 20 kilometers, or essentially from here to Chadstone, right? That's kind of crazy in some aspect. And if you do something like that, what you would find is that you get something that's incredibly dense, really heavy and dense. And so what does dense mean here? If you take a teaspoon of neutron star material, what you would find is that that would weigh 10 million tons, right? And so they're actually pretty crazy in terms of extreme. But these objects don't sit quietly in the center of the hearts of supernova remnants, right? They don't, even though these images may indicate this is the case. And so what we find is that they actually move as well, right? They have motion. And we know that they have this motion is because, one, they leave this trail of bright extended emission as they plow through the interstellar medium on their trajectory through space. And they actually move really quickly, right? So I kind of briefly touched on that, showed that in the previous plot. But what we show here is that they can move anywhere between a few tens of kilometers per second up to thousands of kilometers per second, right? So where did neutron stars get these motion from, right? I just told you that they're producing the massive explosion, but they must be coming from something. Well, the hint actually comes from those extended structures themselves. And so here's a sample of supernova remnants that we know have a neutron star located at the heart of its center. And so these remnants are actually quite special because we can actually measure the motion of both the neutron star, but we can also measure the motion of the bulk of the stellar materials going out into space, right? And that was ejected into the environment. And so here is the white arrow, is essentially the direction of motion of that neutron star. And so how do we measure that motion of that neutron star? Well, we literally take images of the sky multiple times over a long period and measure its position in that image over time, right? And that tells us what direction it's going in. While here, we actually highlight in green is essentially the direction of most of that stellar material that was thrown out in that original death of the massive star. But what do you notice about the arrows, right? You might notice is that the direction of motion of the neutron star and the direction of motion of the stellar material is nearly opposite to each other, right? So what does that actually tell us? Well, that tells us, or this is a signature essentially, that neutron stars get their motion from their explosion because it's going in the opposite direction of the motion of the stellar material. And so what that actually tells you is that even in death, massive stars still have an influence over those objects which are intimately connected to them, much like how our family and our ancestors have to us in our lives. And so the fact that a neutron star can actually move like this is quite important because what can happen is that these objects can wander around the galaxy and find another partner, such as another neutron star or another massive star that will produce a supernova explosion. And so these neutron stars will dance around each other, getting closer and closer and closer until they actually collide. I'll go back so you can see that. And so they'll dance around each other in this dance that lasts for a very long time until they suddenly will actually collide with each other and they'll actually produce another brilliant explosion. Instead of called a supernova remnant, this is called a kilonova. And so when this happens, this is actually the final stage of that massive star, where the leftover remains in the form of those neutron stars are ripped apart and given back to their galaxies, ready for the next generation of star. And so you're probably wondering, have we actually seen this occur in any nearby galaxies? Because what I had shown before was an artist's rendition of what we expect to happen. Well, the answer is actually yes. We've been lucky enough to do this. And so actually, this little burst of light at the top here in this nearby galaxy is lovingly called GW 170817. And this is actually indicated that there was actually the leftover remains of a massive star that had completed its final dance and ended in a spectacular fashion in a kilonova, or another type of explosion. And so when you look out at the night sky and see all these stars glistening in our image, or either at the nighttime when you go look out, right? Just remember that not all is what actually seems, and there is plenty of stellar crime scenes waiting for us to be able to explore. Thank you.
Amazing. You presented it as a mystery, and now I'm like, okay, I want to know more.
Well, we've got plenty of time for questions, so.
Thank you very much for an amazing lecture. As always, I'm sure there's lots of questions in the audience, so I'll give you a second to think of one, and then pop your hand up. We've got a microphone on both sides of the audience, so I'll run up on this side. I'll start with you, so I can put one up first.
You showed us things like iron being produced with gold.
Ah, good question. So gold is actually produced in these kilonova, right? So if you have a gold ring or gold jewelry, that actually comes from neutron stars that exploded long ago, right? Which is kind of cool. So if you ever think about that, you actually have you have neutron star dust and material sitting on your jewelry at the moment. Similar to how like iron, right, is actually in our blood, right? It's a little bit cliche, but we're actually all made of stardust, right? Without stars exploding, we would not be here today, right? And so you can actually thank a lot of these beautiful massive stars for the oxygen we breathe and the iron in our blood, and thank the kilonova for all the really pretty jewelry that we're actually able to wear as well.
Thank you. The fascinating research that you described is what could be called fundamental research, as opposed to research. Such fundamental research has unknown or unknowable benefits in the future. But what do you think, in your personal view, are the practical benefits of such research in the immediate term and in the long term?
Oh, that's a very big question. So in the immediate term is you get images that I think are visually spectacular and really engaging, right? So one thing that is really important is being able to inspire everybody, right, for what we actually do, and let people know that that science here is actually accessible, and we get to study these amazing objects, and they tell us about some of the extreme things that we never have the ability on Earth to be able to study. So they give us a chance to really look at in conditions that we have no idea about on Earth. And so it allows us to really engage people, right? And one of the fun things that I get to do is be able to show what I get to study. Yes, these are some of the images, right? But hopefully this talk was accessible that you could also feel like you could be a part of it as well, right? But a lot of the technologies that go into developing the instruments that actually produce this, right, are leading edge, cutting, right, edge. So for example, these images come from an X-ray telescope, right, which I use a lot, right? And so if you asked me as a little kid if I could use telescopes in space, I would be like, no, that's not possible, right? But I can have a telescope in space point at this. But to be able to have a telescope do that and look at these beautiful objects means that there has to be a huge amount of research and development behind that has not only direct consequences for looking at these beautiful objects, but has consequences for medical research. It has things connected to a lot of industry and everything, right? So a lot of the very fundamental things that we use for astronomy actually have powered your Wi-Fi, right? Have developed things in your phone, your GPS in your phone, right? They all came from, oh, we want to look at these cool explosions, but actually they also have these other amazing developments. And so this type of research has multiple dimensions where it pushes technologies, pushes things very forward. So that's the long-term vision. But on the short-term vision, and also a long-term vision, because everybody should have access to what we do, right? Is it gets people inspired and educate and makes it easy for people to connect at the same time.
My question's more general. It's not about one star, but all stars. How big is the universe?
Oh, it's 13.6 million light years. 13.6 billion light years, I think it is. It's big, right? It's much bigger than we can ever imagine, right? So it's much more larger and larger than just the stars that we study. So most of the stars that we actually look at, like our sun and things like that, we can only really see in our Milky Way or maybe some of the nearby galaxies, right? What supernova allowed us to actually do, all these stellar death, because they're so bright, brighter than our galaxies, we can actually start to look much further in galaxies that are way beyond our comprehension in terms of distance. And we actually cleverly was able to use these bright stars or these pinpoints as light as actually distance markers, right, in our universe, where essentially we know we can work out how bright it is, and that gives us a constraint on how far it is, and that actually allows us to measure essentially the distance of the universe, or how much the universe is expanding. And this was actually won a Nobel Prize by Brian Schmidt, who's at ANU. Thing where you could actually use these supernovae to try to measure the expansion of the universe. But it's big. I guess that's the answer. Beyond what we can ever comprehend.
Thank you for your presentation. Have we discovered new elements from stellar explosions, aside the periodic table?
So no, we have not discovered anything beyond the periodic table. So what you think of the periodic table is a lot of things that we actually already see and we can detect. The issue is whether we actually detect them, and that depends on what wavelength they're observable in, what instrument we're actually looking at. But everything in the periodic table, except I think things that have some of the highest periodic numbers, which are produced in labs and stuff like that, we don't see necessary signatures of those because maybe they're rapidly decaying or they're maybe not stable enough. But everything we see on the periodic table is there. And actually, these colours that we actually make here, even though you might think I'm doing it to make them look beautiful, actually they do tell us about the type of elements they are, where something that is like very blue is maybe more oxygen, and something that's very red or green and maybe more iron in it, right? And so we actually colour code them based on the elements that are actually produced.
I'm going to come here and then there's one way out there, Matt, if you want to fill that one next.
Nice talk, firstly. You just mentioned about elements, and I see you have like traces of elements for like supernova explosion. I'm just wondering if you study like the distribution of elements, let's say in a galaxy, can you combine with like supernova explosion element maps to like study the previous state of like a galaxy? Like things like this?
Amazing question, and the answer is yes. So yeah, you can actually do this. So what you do is that, and this is actually a project that one of my great master students who's sitting in the audience is actually going to be looking at, is essentially you can work out the elements, the amount of elements, and measure how much there are of these in these different remnants. And then you can make a measurement of the amount of elements in the galaxy through independent methods. And you can say, do they match, right? And if they match, right, that tells you that the only way you can produce those elements in the galaxy is that they had to come from stars that died long ago. But if they're different, right, let's say they produced more of something or less of something, that tells you that maybe we didn't have as many massive stars that died, or maybe it tells that like there's something weird going on, right? And that's where you can kind of get into the science of it. But it's a great question because you can absolutely do, and people do this.
Thank you. My question is very light. Do you have a favorite supernova?
Yes, I do. So actually, the ones, I'm so sad that the thing didn't actually work. Sorry about this. But third row, the one on the very last column, right? The one that's kind of pink and looks like a little bit like a Batman symbol if you kind of shut one eye. I stare at these a lot, so that's why. So this is one of my favorites. It's called W49b. And the reason why, apart from being spectacular, it's one of the most extreme supernova remnants in our Milky Way. It is so bright, it's ridiculous because it's so far away, but it's one of the brightest objects that we have in this category. But also what is very special about this one is it's thought to harbour a black hole. So I had only talked about neutron stars, but core collapse of massive stars can actually also produce stellar mass or black holes that are about the size of our sun as well. And so we've been looking for these signatures and we can look at them through different mechanisms, but we've been hunting for them in these supernova remnants because we know that this is a collapse of a massive star. So if they produce black holes as well as neutron stars, then we should see some signature in here. And this is one of the only cases where we've got pretty strong evidence that this is probably true. So I love this one, but there is many. I have lots of love for all of these objects.
Yeah, first of all, thanks very much for your presentation. I found it, through all, not a physicist, just a lay person. I was really interested in this notion of the terrain of space. We talked about that in relation to the stars, that they exist in different terrains. And is the terrain of space stratified, for instance? Is it layered, or is it a single plane? And how is it actually structured, basically?
It's a very good question. So the answer is all of those. So it really depends on what part of the universe you're looking at. So if you're looking in our Milky Way or in our local part of our universe, what you find is that there's material all in different ways, right? Galaxies are very, even though we see an image of it, right, looks pretty stationary. There is motion occurring all the time in that. So that means you get things that are shearing, that means that are moving in slightly different directions and everything like that. But they tend to you get clumps of material as well. So then that means you can find places where stars are born, or maybe where neutron stars are found, or or where you get other parts. And if you're close, for example, to our the supermassive black hole at the center of our Milky Way, which most galaxies harbor, this very big black hole at the thing, the terrain is even more crazy than what you could possibly imagine. Now, that's in a particular galaxy, and this is very common across all galaxies, and people study essentially how the terrain, which is a beautiful description of this, how it actually changes with depending on where you look in your galaxy in different galaxies, and how, when you look out further. In between galaxies, right, that's another question, right? Is there material in the same way that we know between galaxies? And there is material there, but it's harder to probe. And so people are actually spending a long time trying to understand all what's going on in between galaxies and understanding how that space actually changes. So the answer is everything and above.
As we go on, get more and more questions.
That's all right. We've got plenty of time.
We've got a little bit more time. Is there one over there? Otherwise, I'm going to come into the middle here. Was it? No, okay, I'm going to come into the middle here.
Thank you, Professor, for such a wonderful, inspiring talk today. You've talked about different ways of mapping these stellar deaths, and I was wondering if you've ever noted a sonic representation of these deaths. So, in other words, is there a music of the stellar?
Very awesome. Yes. So you can actually hear the music of that. So, I showed essentially how the brightness changes as a function of wavelength, right? You can easily map that to sound to understand and hear the sound of our universe. And people actually do this. There's an astronomer actually in the US, and I forget blanking on her name at the moment, but her first name's Wanda, and she actually, she's visually impaired, and she actually does astronomy by converting all the signatures we have here into sound and hearing things, and it's beautiful. And so you can actually look up online, right? They actually have, for example, for that kilonova where the neutron stars are colliding, you can actually hear what we call the ring up, right? Where you hear essentially they're getting closer and closer, and then it, ding, there was a neutron star collision together. And so this is a really fascinating area and something that really is really inspiring beyond seeing these images. And then I know that there is a number of, we work very closely also with artists, right? To essentially take these beautiful images and put them into dance and song and really connect it also in addition to that other part that really inspires us in our lives, right? The music, the sound and everything, and try to connect it. So 100% yes, absolutely, it's beautiful.
When the critical mass of the star, the critical amount of iron is reached in the star, is anything known about the timeline as to how quickly the star collapses?
Yep, one day.
One day?
Yep. So one said it's very, very quick. It's like, because think about the lifetime of a star like our sun, like more massive than our sun, right? These lifetimes are hundreds of thousands of years, right? And they burn hydrogen and helium quite happily. But once it starts to get heavier and heavier elements, the timescales start to rapidly evolve very quickly. And so you might only, the other levels, it may be kind of like, a few thousand years or something like that. But once iron is there, right, that rapidly evolves and rapidly and then within a day, it can be too much and it goes. And so that's why we look for these signatures prior, hoping that we may actually see something that could give us an indication, oh, that's about to go off, let's point our telescopes in preparation, right? Because it happens so quickly that the only way we can see all those pinpoints of light that I had shown in those images that we took in Hawaii is that we have to monitor the sky constantly. So there's multiple telescopes around the Earth at the moment that are taking images of the snapshots of the sky every night and then comparing it to the night before to say, did we see something different? Right? And then that then gets triggered essentially to an email or to me or something, or my ding on my phone saying, go have a look, do we need to get a spectrum, right? Which is essentially, what's going on? Let's go have a look. Is this true, right? And so it happens so quickly. And so we're looking for ways of trying to predict this as well. So this is why we looked at both the pinpoints of light and also looking at the stellar death many, many years later to try to map the whole history from during its life and afterwards.
I think I saw there was one more on this side somewhere. Oh,
and there's also one here too, yeah. Oh, sorry.
For the sake of time, this will have to be our last question.
Yeah, that's fine.
Okay, we'll be around for a few minutes for some very quick urgent ones only afterwards. Go for it.
I was just wondering if similar techniques have been used to dictate when new stars are being created?
Yeah, so actually yes. So not necessarily in the same way, because new stars don't suddenly burst into life like this. It's a slow accretion of material from essentially things we call stellar nurseries or big clouds of molecular hydrogen and helium that start to rotate and slowly will collapse and gain material slower and slower and slower, and then produce a star that essentially gets beyond a critical mass that it actually starts the fusion of hydrogen and helium. And so it's not essentially looking for that big burst of light, but what happens is that people looks at galaxies or looks in our local universe and they take images of parts where we know stars are born or where there's these big clouds of material waiting to be converted into a star. And we look to see if we see indications of a light kind of peering through the dust or the material that we look at, and then we can monitor them. But good question.
Okay, I know there's a few people who have more questions and things that they would love to say to Katie, but unfortunately, for the sake of time, I'm going to have to cut us off there. But if you could please give Katie a massive round of applause. Thank you so much for all of you for coming. Welcome to those of you for whom it was your first July lecture. They happen every year, Friday evenings in July, so have a look out for them next year. And have a great winter, and we'll see you next year. Thank you, everyone.
Thank you, everyone.
Makes a